Good morning. It's a great pleasure for me today to introduce our speaker, Mikhail Lukin. I think he's a person who doesn't need an introduction because we all know all his important contributions to the field. I want to mention that Susan Yelin is also in the back. They are visiting both from Harvard. Well, Misha has revolutionized our understanding of atomic systems. He has introduced very pioneers ideas on how we use, for example, Rydberg atoms for quantum information, how we can use MB centers for different applications, including sensing. He has done beautiful experiments lately on Rydberg arrays, and it's such a great pleasure to have Misha here. I had the pleasure to be at ITAM and work with him as a postdoc, and really inspiration. So it's really great. We will have here for a very short time, but it's great that he is giving us a talk today on exploring frontiers of quantum science using programmable atom arrays.
Thank you, Ana Maria. Thank you so much, Ana Maria, for a great introduction, and thank you guys. It's so great to see you all in person. So I actually do have one small request. So it's kind of a remarkable thing. So I thought I have these cables for all, case, but I need one more. I ran out of. Okay, so I just need to get here. Amazing, you guys. Oh, wow. Okay, thank you so much. So yes, so okay, so okay, so I will tell you a little bit about our work using arrays of neutral atoms to basically kind of explore building quantum machines and figuring out what to do with them. And so this work is a part of the effort that many of you are involved in. That, so I think it doesn't really need kind of a big introduction. So in this effort, what we are trying to do is we're trying to isolate and control some simple quantum objects, and then build more and more complex systems from them. And using this kind of systems, what we hope to do is to explore new physics, and you will see some examples of creating and probing new quantum states of matter, but also start exploring new applications, in particular applications for computation, communication, and metrology. So, and of course, this is now a very exciting field. You kind of read about this field almost daily, but it's actually worthwhile sometimes to kind of stop, step back a little bit and realize that there are two big challenges that the field is facing. So despite all of this kind of excitement, we do not yet know if and how we can build truly large-scale quantum systems containing millions of qubits, and keeping them coherent and quantum mechanical. And what's even more shocking, perhaps, is that even if someone, one of you guys, or someone in our group, build an amazing big machine, and I want to give it to you, you would actually not know really what to do with that. So that's another challenge which is facing this field, is how we can actually use this large-scale quantum system to achieve useful quantum advantage. So but you could say, well, with these two big questions, why is it why is there so much excitement? So, the reason is that, I think there is actually a very special time in the field. And basically, this is a time of, I would call, kind of ultimate quantum rivalry. And this is sort of can be understood in many ways, but I think it's actually sort of much more, I'm thinking about it in a kind of much more like Eastern philosophical way. So this is basically a competition of two forces of nature. And these are the forces of controllability and scalability. And these forces actually are present in many areas of human kind of and scientific and technological kind of interactions. So for example, if you, took a bunch of, geo-educated physicists and put them in one organization, this organization by definition will be very hard to control, right? So, and it's the same is true actually in a way in the quantum domain. But what is actually now happening is that we can now build systems which are big enough, programmable enough, and quantum enough that we can really start tackling these kind of challenges. And this is basically kind of a current frontier. We would like to really push these systems beyond what kind of modern classical computers can do. So it's in reality kind of requires basically controlling over 100 or so of quantum bits, and then uses systems to figure out how to build bigger and better quantum machines, but also start exploring some early kind of applications and algorithms and things like this. And with that, I would like to kind of advocate that we are now a little bit in the age of quantum discovery. And I hope I have enough time to show you some examples of where we can use machines to really do things, which we have not kind of, we could not predict otherwise, So with that, the plan for today's talk is basically to give you a little bit of an overview how we actually build these quantum systems atom by atom. And of course, here with in particular Cindy and Adam's group, many of you are experts. So I'm sorry, there is a kind of I think somehow the system is a bit slow. And then, okay, so then basically what I will do is I will kind of try to give you examples of, from the modern kind of frontier of this field, in particular, some of the work that we have been doing recently involving control of two-dimensional systems, exploring quantum phases and phase transitions, but also kind of realizing new states of matter, like, for example, quantum spin liquids, and also a little bit applications of to solving computational problems, applications to so-called quantum optimization. And then at the end, I hope I will we'll have a little bit of time to tell you about basically new architecture for quantum computing that we have recently demonstrated. And I think it's very exciting, very special kind of approach. Okay, so in our approach, we build quantum systems literally atom by atom, and we are following in that by some pioneering work which was done here in Gila by Cindy's group in particular. So what we do, we basically start with the gas of the atoms pre-cooled by using conventional laser cooling techniques, and then we shine focused beams of light into the vacuum chamber, which act as optical tweezers. And they are focused tightly enough that each tweezer can host at most one atom. So, but in what we do is we don't start with just one beam, but we start typically with many, with actually hundreds. And in each given shot, each tweezer, being either loaded or not. And so there is some entropy in the system. To get rid of this entropy, what we literally do, we just take a picture of the atoms, figure which traps are filled and which are not, and then basically remove the empty traps, and then rearrange the remaining traps in any kind of desired configuration. And so with that, we end up with the atoms which are sitting a couple of micrometers away from each other. So they're basically, at this point, they're non-interacting, they're completely classical. And in order to basically make the atoms interact, what we do is we excite them into the Rydberg states, into states with high principal quantum numbers, and that way we can actually engineer interactions. And this is our joint project together with Marcus Greiner group at Harvard and Vladan Vuletic's group at MIT. So I want to maybe briefly talk about the atom interactions. And if the slide will to change, is so we basically like the Rydberg atoms because they have long time and lifetime and very strong interactions. So in particular, if we excite to the atoms to the principal quantum number on the order of 100, the interactions, the van der Waal interactions between Rydberg atoms are larger than those in ground state atoms by 14 orders of magnitude. 14 orders of magnitude is a big number, and we can make a good use of that. So in particular, if we derive atoms on resonance, if they are far away, initially they would just, undergo independent radio oscillations. But if we bring them close to each other, then there is, at some point, this interaction just takes over. And so if you try still to basically derive the atoms on resonance, at some point you will be able to excite every one of the atoms, but never both, because of this very large shift. And so this effect, where it involves blocking of more than one excitation, is an essence of something which is called the Rydberg blockade. The idea that we developed together, so with Peter and Ignacio and other people about 20 years ago. And we actually like this Rydberg blockade, the fact that the excitation is blocks smaller by a distance smaller than this characteristic radius. We call it blockade radius. We like to use this effect because it allows for very robust entanglement and manipulation of atoms. So basically, once the atoms are closer than this Rydberg blockade, then it doesn't really matter what the distance is to the leading order. It doesn't matter if they move or not. So, and that actually allows, it becomes kind of very forgiving for us to basically kind of, create entangled states, for example. So together, so the procedure that we'll use in most of the experiments is that we will prepare some, regular arrays of atoms, and we'll subject the atoms to pulse sequences, and it could be either hyperfine state manipulation or Rydberg manipulation. And then at the end, we will do some projective readout. Basically, the one effect that, one type of application which will be heavily featured in this talk will involve the application to programmable quantum simulators. So this is actually really pretty much following the kind of original idea by Feynman almost 40 years ago. So in this case, what we'll do, we'll implement effective spin model. So we will basically start with atoms, for example, arranged, like shown here in a regular line, and we'll try to drive them, simultaneously to the excited state. And so all of these processes will be described by this Hamiltonian, which is shown here. So let me just, kind of illustrate different terms. So basically, if the interactions between atoms are negligible, then it's just normal rabbit driving with detuning. And you can ask, what's the ground state of this Hamiltonian, which is a lower state? Of course, this lower state will be kind of effective dress state, will depend on the sign of the detuning. So if the detuning is negative, then you would favor all atoms being in the ground state. If the detuning is positive, you will favor all atoms being in the excited state. But of course, the state like this is not compatible with Rydberg blockade. So for example, if just nearest neighbor is blockaded, then what will happen is that, basically you will not be able to excite nearest neighbors, so you will excite every other atom. So that means that the ground state for this positive detuning will be a state up, down, up, down, up, down. This is a state which has antiferromagnetic order. It's so-called, Z2 symmetry broken state. But if you now extend the range of blockade, then you can excite, only every third atom. So this, up, down, down, up, down, down. So this is a state with Z3 broken symmetry. And then, you can also kind of extend it, to higher interaction range. And, this is a state with Z4 broken symmetry. And basically, we can explore this phase diagram very easily by just starting with all atoms in the ground state and detuning being negative, and then try to adiabatically, change the detuning to enter all of the states. And so this is a kind of procedure we often use, not always, but often use in our experiments to explore various many-body states. And in this example, this is actually very easy to see how, like, not only, what kind of states you create, and this is this antiferromagnetic up, down, up, down, up, down. So this is a state with every third atom excited, and and so on. And basically, all these states in this case differ by just initial position of the atom. So we excite the atoms to the same Rydberg states, in this case 70th state. But here, for example, the atoms are sufficiently far away that only second nearest neighbor, only nearest neighbor is blockaded. So here, they are brought closer. So you can only excite every third atom, and here, you break this Z4 symmetry. And so basically, these are the pictures where you also see basically a phase transition. So if you now go into the detuning close to zero, what you see is basically a competition of the state where all of the atoms are in the ground state, and there is order emerging. And so these are these kind of fluctuations, quantum fluctuations, which drive this transition. And so all of that can be explored very easily, by just kind of moving atoms around and picking which Rydberg state you excite. So this is a kind of system that, over the last, couple of years, we were able to explore a wide variety of different aspects. So we could, for example, use it to make quantum gates. We could also, in a large system in 1D, we could explore phase transitions, kind of looking at this, in particular, this transition between, like state which is called disordered, where all atoms in the ground state, and the state where some order emerges. So we also explored non-equilibrium dynamics by basically kicking the system across the phase transition and seeing how it evolves. This is connected to something which is called many-body scars. I might be able to talk a little bit about it in my end of my talk. And we also explored creating large entangled states, like in this case, a GSG state. So basically, all of these kind of directions are closely connected because they involve coherent, high fidelity either analog or digital evolution. And this is just like which way we use it just depends on what kind of pulses we program. So I should say also before proceeding is that in the past few years there is a kind of new generation of fantastic experiments, and including some here at Gila in the lab of Adam, which are really kind of pushing this work in many different directions, including different types of atoms, and now also even molecules. So, and I think this list is by now way outdated. So there are many more experiments already going on and being planned. So, okay, so it kind of brings me to maybe a point where about like 2 years ago, we actually stopped our experiment and we undertook a major upgrade. And so now in our lab at Harvard, we are running what we call generation 2 atom array. And this generation 2 experiment is basically powered by a special light modulator. So it's basically a computer generated hologram, which allows us to create arrays of thousands of traps, which when we project them into the vacuum chamber, as it's shown here, basically we can take a picture as a very uniform, large scale array. So the disadvantage of these SLMs is that we cannot kind of switch them very fast. So to move atoms around, to sort atoms, we use actually 2 crossed acousto-optic deflectors. And when we kind of program them with AWG, we can basically move columns and rows atoms around in a highly parallel way, such that we create, basically large arrays of about 300 atoms or so. And then we basically, about 2 years ago, we kind of finished this upgrade, but then you all guys know what happened. And in fact, this is remarkably 2 years ago. So it was the last kind of day in our lab where we basically could have a normal operation. Then we actually had to shut down all of our labs for maybe 2 months, an order of 2 months. But there were 2 positive things. So first off, we had 1 week warning that we had to shut down our labs, and then we were told that we will be allowed to run servers. So during this 1 week leading to this event, this amazing group of people actually converted this experiment into the server. So basically, since that time, we ran all of our experiments remotely, and it's basically running nonstop. And it has been a very special time in our lab, and you will see maybe why in a few minutes. So basically, to just kind of start, we can create, all of these different configurations of atoms, and we can also create arbitrary patterns. So for example, suppose you would like to have a pattern like this. So you just program it, press a button, and here comes the atom array, maybe, You have to wait, for good things. So yeah, so here it is, And so basically in practice, what we can do is we can, create arrays of up to about 300 sorted atoms. And if we kind of tune everything, optimally, so we have like each trap filled with 99.5% probability. So 99 is kind of standard, and we can push it a little bit more if we want. So, okay, so what can we do with that? So let's just kind of consider an experiment very similar to what I told you before in 1 dimension. So suppose we just want to explore quantum phases in 2D in a square lattice, the simplest arrangement. And so basically, if we just, have a situation where we have nearest neighbor blockade, so then what will happen is that you should be able to excite every other atom. So it should be also an antiferromagnetic pattern. So in fact, in this case, it will look like a checkerboard. So it will, the space, we call it a checkerboard phase. And actually, it turns out that if you now start playing with this blockade radius, blockade range, even in this very simple geometry, you can access a wide variety of phases. And these are the sum of phases which have been predicted by Ryan, who is actually a student of Subir Sachdev. And it results in this very complex phase diagram. I should say by now we have seen most of these phases in the experiment. But even the simplest, turns out even the simplest transition from this disordered phase, trivial phase to this checkerboard phase, which should be a 2D, it's called technically 2+1D Ising quantum phase transition. It turns out it has never been observed. So let's see what we can do about that. So, and again, what we'll do here is, so what we'll do is we'll start with atoms arranged in this kind of square geometry, adjust blockade radius appropriately, start again with all atoms in a ground state, and then just change slowly the detuning from negative to positive, and then on some shots, we, in this case, we create a perfectly ordered, 2D pattern, for up, down, atoms. Well, admittedly, this is not always, the pattern which comes out. So one has to kind of, do some statistics and so on. And actually, in this case, what one can do is one can try to, for example, evaluate a correlation function. So again, this correlation function is density correlation function, shows this up, down order, which basically extends across the entire array in this case. But we can also look at the system microscopically. And you can ask, so, on each given run, with what probability can you basically obtain a given pattern, a given microscopic state? And in fact, it turns out even though these states do not appear very often, it's still their most probable state. A state like this and a state with complementary order are the most probable state. And the probability of the states grows down exponentially, but it actually goes down with a probability of like 0.97 to the end. So it basically means that with about 3% per atom, we have some kind of error in the system, but this error includes now everything. It includes, imperfect adiabaticity, it includes quantum fluctuations, because the state at n is not completely classical. So it kind of allows us really to benchmark the system. Yeah. Yes. 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 No, we tune detuning, which no, it's a quantum. We have transverse. Yeah, but it goes across a quantum phase. We have transverse field on. It's big, it dominates. It dominates. But then we change the. Sorry. So yeah, so we have in this language we have X field on. And then what we do is we change Z field. Z field. We change longitudinal field. Exactly. So this is a second order quantum Ising phase transition. But of course, this initial state and the final state are both classical. That you're completely correct. But in yeah. No, we do. And in between, it's exactly what happens. And in fact, I will show you now that, indeed, so we can, okay. So, but what I mean, what Leo, your point is actually a good point. So you say, okay, this initial state is classical and the final state is classical, right? There is something in between, but how do we know? Is it a classical phase transition? Is it a quantum? Can we check that, right? And that's, like the question, can we really observe and study this Ising phase transition? So. No, it's a one. It should be a one phase transition here, and it should be Ising. It should be an Ising universality class. It's not exactly solvable, but it should be a phase transition in Ising 2+1D universality class. So, and here is how we show it. So we can study it experimentally. The way how we do it is so this Ising quantum phase transition should be characterized by these critical exponents, by all of this universality stuff. So the exponents for that have been calculated, but apparently have never been measured. So let's see what we can do about it. So to study that, what we do is we basically go across this phase transition at variable speed. So what does it mean? So if you go very slowly, then you create an order across the entire array. But if you go quickly, you create correlations locally, but then these correlations don't have time to propagate. And it's actually quite dramatic what happens. So here is, if you go slowly, here is the correlation function. Here is if you go quickly. And so what we can do now by just looking at these correlation functions, we can try to extract this correlation length. And this correlation length now is extracted as a function of speed, but also at what detuning we stop, right? And here in particular are this, this point that actually, this point where Leo is asking about, here it should be dominated by quantum fluctuations. So, and in order to kind of extract these exponents, we use this idea of universality, which actually tells us that if we rescale all of these curves with the speed with which we go, then they should all collapse. And so if we do this rescaling, and this collapse should be basically given only by this, by this critical exponent. And so if we do this rescaling, indeed, we have actually a very nice collapse. And in fact, by optimizing this collapse, we can extract these critical exponents, Z actually nu in particular, and basically this critical exponent which we measure is in a very good agreement with the quantum phase transition prediction. It's different from classical and also from quantum in lower dimension. So that's how we, and we have done kind of very careful analysis of that. That's actually how we know that, in fact, what drives these things are really quantum fluctuations. Does it make sense? Yeah. So these exponents, I believe, are computed numerically, but someone like Leo should know. So these are not, so we are not, so they're not exactly solvable case, but it's basically 3D. It's exactly the way how you do it. So you map this into 3D Ising, but even for 3D Ising, classical, it should be computed numerically, right? That's right. I see. But I mean, the point here is that, okay, we did not measure many digits, but it is clearly different. I think like the classical predictions are, I think it's 0.5 or 1 or something. So it's different from both classical predictions and quantum in lower dimension, which actually turns out also to be important, because you can ask, what is it really a bulk which drives it, or boundary? So these are the questions which we actually now can ask and answer. Yes. So yeah, in this specific set, we actually assume Z to be equals 1. So we have actually independent ways to also extract Z, and we have done it. Of course, the accuracy is a little bit worse. Yes. We tune the detuning with transverse field on. Yes. Exactly. But the symmetry broken, but it's a. Yes, that's exactly right. Interaction is stronger and transverse for nearest neighbors. Yes.
So there's another axis.
Oh yeah. Oh yes, and that's exactly, and that's what gives rise to all of these, exotic, phases. We have studied them as well, actually, and we have. I'm not going to talk about it today, but we have observed most of the phases we try and predict it, with maybe exception of one. We actually observed. And we also studied phase transitions, actually very interesting, because for some of these phases, phase transitions predicted were first order, but we still observe them. And it turns out that they are dominated often by boundary. It's like when ice, grows, if you have some, or, if you grow a crystal, if you have some seed, you can grow that. And we can actually, we can see, for example, we can distinguish boundary transition from bulk, And these are the kinds of stuff, so, okay, but you already kind of see that, starting from that point, we can really kind of enjoy a variety of explorations. And so this is, for example, one of these phases, which we observe is kind of non-trivial phases. So in fact, some of these phases, they have even finite amount of quantum fluctuations in a kind of ordered state. But of course, we can also do other things. So in particular, in addition to just going slowly across the array, we also could do, basically quenches, and we studied non-equilibrium response. So we also studied what happens in the systems which are frustrated. I'll talk a little bit about that, and that's, that way we could probe spin liquid. So we also now started studying disordered systems, and actually it's very interesting because it's kind of related to solution of combinatorial optimization problem. And so we also are working towards building large-scale quantum computers. And actually, the other development is we across the Charles River, we have a startup company, Query Computing, which actually has its own machine, and very comparable to what I've kind of showed you. And in fact, starting in June this year, you will be able to access this machine on Bracket Cloud. So okay, so at this point, I could pause a little bit. So at this point, I could talk about all of these things, and it will take more than an hour. So I'll just have some small sampling, of the things we have done. But I'm also happy to answer any questions if you have. Okay, so then I will just go forward, but feel free to interrupt. And so the thing, yeah. 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 So this here, it's mostly determined by how slowly you go across the phase transition, right? So it's a correlation function, across the entire array. So at this point, if you go, like slow enough, then there are some boundary effects which start to dominate, and they are factorial. So at this point, the correlation length basically kind of becomes comparable to the array size, and there are some, for example, like the ways how correlations grow, they can be nucleated from the middle, but there are also edge effects. And so these are kinds of stuff for this simple phase, they are like to the leading order, not significant, but from some other phases, as I mentioned, they completely dominate the transition, it turns out. Yeah. Well, that's not, that's not here, to be honest, is not so clear. So here it's kind of, apart from this boundary stuff, it kind of is Gaussian or something. It's not a, so, yeah.
Can you help me to understand, you've got this 3% error
Yeah.
per
Yeah.
atom. So
Yeah.
I look at some of these correlation functions, maybe they look like 10 by 10.
Yeah.
Where it
Yes.
try to think of it as it affects the signal to noise, but you're figuring out the length scale of the correlation function.
Yeah.
So it's just a question of signal to noise on that fit. You can overcome that with just more data.
Yeah, I mean, yes, no, it affects signal to noise, but it, of course, if you have a, certain kind of error probability, it will also determine your correlation length eventually, right? If you, if you start, I guess, in 1D, right? If you have 3% error, right, you will have, after like 30 atoms you saw, your correlation length will, it will stop growing, right?
So maybe so then should I understand that kind of for the correlation links that are on that plot,
Yeah.
that essentially you're still in the low error limit.
Exactly. So in this case, exactly.
That's not extending out to like 100.
Exactly. It says, yeah, exactly.
So
Exactly.
you're still kind of like
It's still limited. In this case, we specifically work in a regime where it's still limited by the speed, right? Because it's what we want to extract, right?
Okay.
And it's kind of, it's big enough in this case, right?
But on the other hand, it says something like if you really want to measure this correlation function, that's very long.
Exactly. Eventually, these errors start to play a role. And, as I said, these errors, it's kind of, I mean, like part of that is intrinsic quantum fluctuations because we ramp to the detuning, we still have field on. So it's sort of, we're not measuring in the right basis. One could in principle improve it and so on. But part of that, we know there are some spontaneous emission and stuff like that, right? So, yes. Yeah. 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 So this is, it's an excellent question. And I kind of maybe said it already kind of quickly. But so, for example, for this data, we specifically work in a regime where this finite size effects are not kind of very, significant. We sweep, slow enough, but fast enough, and so on. And so basically, like what it means is that for this anti-ferromagnetic phase, we can basically work in a regime where bulk phenomena dominate. But for example, some of the other phases, and we have actually a couple of papers now on this, but so for instance, this phase, which is shown here, which you will see is kind of event interesting. So it has this kind of funny order. It has a kind of super lattice. And then in the middle, occasionally there are some atoms. So there is a pattern, but there are some things which kind of break this pattern. But if you, for example, look here, so this picture is actually will tell a story. But you look at here, look at the boundary. The boundary is almost perfectly Z2 ordered. So when we took this data, we just, okay, we see this, bulk boundary and so on. But now we understand that for this transition, and this is a transition into the so-called striated phase, is actually dominated by the boundary. The reason is because the bulk transition is the first order, and the boundary transition is a second order. And so basically, this is like the example where, it's like what I said, if you grow the crystal and you have some kind of seeds, these seeds allow you to grow much better crystal. So in here, boundary acts as a seed. So these data are completely dominated by the boundary. And it's a little bit of philosophical question, which we did not settle with Subir, to what extent, like, is it really sort of a finite size effect or not? Because I believe that in this case, because the bulk transition is the first order, the boundary will always dominate, no matter how big the system is, or at least, for very large, up to very, very large sizes, right? And these are the things you can study now, with this. Yeah. Well, no, it's about 200 to 300. Yeah. Yeah.
So I'm just wondering if you can also prepare like that state.
Well, we can potentially, and we did it in one dimension. But for example, in one dimension, we did it up to like 20 atoms or so. We really prepared by going across the phase transition slowly enough. We actually prepared the cat state. So and I think now we improve the fidelity and so on, but for like to prepare 100 atom cat state is challenging, so maybe we could do like 30 or, but indeed it is, and like in some of this, but like the classical signature of that I've shown, right, that we had two patterns, right? And basically with almost equal probability, we had two perfectly. Oh, yes. I've kind of went maybe a little bit too fast. So here is one pattern, right? And so here, basically this is number of occurrences. So one pattern is most probable, but very close to it is another pattern, which is just shifted, So this is exactly what we see. So we really see symmetry breaking. Yes. Well, we can certainly go lower, right? So you will see a little bit later, which actually we can go to arbitrary dimension in principle now. But okay, we will see it will be done in different ways. But for that we have to get to the end of the talk. So no, that's okay. But that's a great questions. So this is that's a benefit of in-person presentation. So okay, all right. So I'll give you with all of that. I will give you. Oops, I think now I talked too much. So I'll give you a little bit of sampling of stuff that we have done recently. And the first thing that I will tell you is an example from a kind of, which is, very much condensed matter, which is related to this field of topological spin liquids. So, so what is that? So this is basically an idea, which is, 50 years old, which was put forward by Phil Anderson, who basically almost postulated that there could be some states of matter whose properties are not determined by some kind of local parameter, other parameters, by determined by systems topology. And I was told by Federico Capassa, who was at Bell Labs at the time when Phil Anderson came up with this idea. He was very accomplished, scientist already. He gave a seminar on that, and people told him, you should not really kind of talk about that kind of stuff, And so, and he took it to heart. So this first paper was in some kind of proceedings of, materials research bulletin, but actually it turned out this visionary idea had a lot of sort of inspiration. And so actually it really became kind of a big field in condensed matter physics. And kind of fundamentally, the idea is the following. Suppose you have a system which is frustrated in some way. So for example, suppose you have antiferromagnetic system on a triangular lattice. And so you would like to put, this spin up, for example, then this spin should be down, but where do you put the third spin? You don't know where to put it up or down. And so what people then kind of, theorized is that in systems like this, what would happen is that the spins here on this kind of adjusting sides will form entangled pairs like a singlet states, which called dimers. And basically, the final state of the system will be essentially the state where all of these dimers cover the entire lattice. So, but because there are many possible configurations of these dimers, so basically the state should be a coherent superposition of all of these possible dimer coverings. Now, about 20 years ago, thanks to the work of Alexei Kitaev, this field actually received sort of another boost, and in particular, he pointed out that states like this can really serve as a basis for fault-tolerant quantum computing. And the most famous example is this kind of toric code, where basically you have some sort of frustrated interactions, and then kind of you look locally, the system is completely disordered. But if you start measuring, for example, correlation functions which are product of Z and product of X operators, then all of these correlation functions will actually have unique value. In fact, they are, language of quantum information, they are stabilizers of the so-called toric code. But now, kind of despite of all of the kind of work of theoretical work and experimental attempts, up to now, I think it's fair to say that there is no conclusive experimental evidence of such states present in any system, at least to date. So, okay, so let's see how we can kind of address this problem. So, and it's actually, we were guided very much by theoretical work by Subir's group and by Ashwin's group. The idea is the following. So let's place the atoms in this funny lattice. So basically, these atoms are placed here on links of the so-called Kagame lattice. And let's adjust the Rydberg blockade such that one atom will block 6 of its nearest neighbors, like shown here. So basically, if you excited all possible atoms subject to blockade constraint, in this case, the excitation fraction will be 1/4. And so basically, in a lattice like this, what you can do, you can basically map this into the model of these dimers, which I just introduced before. In this case, each Rydberg atom can be viewed as a dimer living on this link. And because of blockade, these dimers will be always arranged such that no two dimers touch each other, like what is shown here. And so then, Ashwin's group in particular made a prediction that, under these conditions, we should create a state which is a superposition of all of this dimer covering, which will be basically like, a spin liquid state, basically a classic Z2 spin liquid. Exactly. One Rydberg atom here corresponds to a dimer, right? And the prediction is we should have basically this type of superposition. Okay, so how can we actually, probe that? So the idea here is that we start with experiment with the atoms sitting on these links as shown here, and then arrange the Rydberg blockade, do this adiabatic evolution again, and then take a picture. And what you see here is one of the many possible outcomes, that you see basically these Rydberg atoms, which I now mark as dimers. It kind of looks like there is a kind of, some kind of dimer state, but then you do this experiment again, you get a different state, So basically there is no, if you try to look at locally for some order, there is none. So how can we study this kind of topological order? And one idea first is to kind of, follow a little bit what is done in condensed matter. So you, for example, can do this adiabatic sweep and kind of try to stop at different points in the sweep and try to see, for example, where you will have some kind of plateau at 1/4 filling. So this plateaus is typically, what, you look, for example, in quantum Hall states, or, for example, people who look for Majoranas, they are looking for this plateau, essentially, And, like this robustness of this plateau, in a way, is a signature that something is happening. But if you look here, there is something is happening at 1/4, but actually it's not so clear, right? And, like, okay, but of course we can do better, right? Because now we have access to the entire, basically, wave function, which we can sample. And so what we can in particular do, we can evaluate these string operators, which are basically products of this kind of local observables, like, for example, in a toric code, this product of Z and X strings. And in particular, the Z string operator here is very easy to understand. So imagine you have a perfect dimer covering, and you just make a string which kind of goes around one of these vertices. So if the state is one of the dimer covering, so what will happen is that the string will cause one Rydberg atom, right? And it means that this, this product of all of those operators will be -1. So if you now make a bigger loop, what will happen is that you will have basically the expectation value of -1 to the number of enclosed vertices, right? And this will kind of indicate again that you have this dimer order. So in a way, it's actually parity of dimers here along the string is effectively a Gauss law in an effective like emergent lattice gauge theory. So okay, so that we can do very easily just looking at different loops. And indeed, what we see is that depending on the loop that you look, you see parity kind of signal non-zero and with a different sign. And in fact, while for larger loops this parity decays, you see that for large enough loops, for basically a fraction of the system size, we see a non-zero signal. So what it indicates is that we basically make a transition into this approximate dimer phase. Okay, but that was an easy case. So we now need to also prove that we have this superposition of all of these dimer coverings. You would say it's very, very challenging, and indeed it is very non-trivial how to do it, but it turns out it is possible. So for that, we need to evaluate this off-diagonal string operator, the operator X, which acting on some of these little triangles will actually shift the Rydberg atoms around. And it turns out if you define the string operator in this way, then if you look at a closed loop, then what act on a closed loop, then what this operator does, it basically takes one dimer covering into another. So I know it's complicated, but just, compared to the single qubit, this operator plays the same role as sigma X. Sigma X takes 0 to 1, and basically if you measure non-zero expectation value of sigma X, you have a superposition. So if we now look at this closed loop X, and we measure it and it's non-zero, we know that we have a superposition of this dimer covering. So, and it actually turns out we can actually measure this X. In order to do it, we have to make a kind of a collective rotation. So we basically can transform the Z string, which we know how to measure, into X string by basically acting on small triangles, and just rotating this kind of collective, state of the free atoms. So experimentally, it's done by changing dynamically the blockade radius, and and it's easy to do, except for you have to change dynamically your intensity of your driving field by a factor of 200. So, and you can talk to Julie and others about how to do it. So, but at the end of the day, it actually worked out, and what we observe from this is indeed non-zero signal. So we see that we have a kind of non-zero coherence across the kind of a wide variety of loop. Again, loops extending by the to the fraction of the system size. Okay, so we see a signature between dimer coverings. But now, how can we use these tools to really check if they have a spin liquid or not? So in order to do it, we basically study topological properties of this system. So in particular, what we do is we compare the closed loops and open strings. And this is, maybe the best signature what we have seen the spin liquid. So specifically, if you look, for example, for loops of comparable system size, if the loop is open versus closed, you see quite dramatic effect. So here for open loops, basically the signal is exact dead zero, and the closed strings have a finite signal. So likewise for X strings, there is a parameter domain where basically these closed loops, have a finite signal, and open loops just dead zero signal. And so basically you can actually formalize all of these considerations. So you can formulate it in terms of this FM or BFFM string order parameters, which people have kind of developed as a really formal tool. So it basically compares open strings to the closed loops, and essentially these other parameters can distinguish trivial phase, quantum spin liquid, and these other phases like a valence bond solid. And indeed, what we find is in some parameter domain, we have basically the signatures, all signatures corresponding to the onset of this quantum spin liquid phase. So at this point, you could say, well, okay, so this is very nice. You can see it. I mean, was it actually worth to do this experiment at all? It actually turns out the answer is yes. And in fact, as we kind of was trying to do the experiment, we also tried to push numerics to the limit. And actually it turned out that if you sort of do numerics properly and look for the ground state, then what you find is that actually under the conditions where we observed the spin liquid, we should really not have seen it. So in fact, what happens is that long range interactions, it turns out, destabilize the spin liquid, and the ground state, at least under the conditions which we have used in our experiment, basically should be what's called valence band solid. So it basically should be like patches of these dimers locally resonating, but the coherence should not extend across the system. And this is not what we observed. So it would have, for example, different, these BFFM order parameters should not be zero in this domain. Yeah.
Just related to when you were measuring the coherence, how long does those coherence last? In some sense, you're dragging it to stimulate.
That's right.
Dynamically, right? It's not like
that's right.
And because it's not so long, you're supposed to destroy that.
That's right. So it actually lasts. It basically lasts as long as this kind of Rydberg array lifetime, right? So it's basically it lasts for like as long as we can meaningfully do this control experiment. So basically it lasts for the entire. I mean, in practice, it's a few microseconds, but basically this is as long as the atoms in Rydberg state sort of live before they fly away, So, and why do we create this spin liquid state in the first place? So what we have done, then we try to do kind of like numerics a little bit, and for a smaller system you can still do it. And actually, it turns out that if you do this adiabatic preparation, indeed, you enter into the state which has basically signatures of all signatures of spin liquid. So basically, what we understand, the way how we understand it now, is that the transition into this valence bond solid state is a first order phase transition, and transition into the spin liquid state is a second order phase transition. So if we go across the phase transition with a finite speed, means slow but not exponentially slow, basically we just pass through this first order phase transition, we just don't see it. So in a way, kind of, it's very similar to this, what happens, for example, in typical BEC experiments. So in a BEC experiment, you cool to the state, which is actually not a ground state. The ground state is a chunk of solid, right? And this is exactly what happens here. And in fact, there is now new kind of inspired by our experiments. There are some new theoretical studies which predict exactly that we should create this long-lived metastable spin liquid state. Yes.
So is this the same thing with the model with only nearest neighbor interactions is critical? That's why it's small for division speaking.
It's not, no, if there are short range interactions, you should obtain a spin liquid, but in a parameter domain which is significantly narrower than what we observed. So, and there is nearby phase, which is, valence bond solid, right? So, but basically, the transition to this valence bond solid is always first order phase transition. And, basically, if you go with the finite, if you go across a phase transition with the finite speed, or at least with speed which scales, say, linearly with system size, right, you just don't see it, you just go across, and this is the result of now better numerics, and like and kind of it's our interpretation, right? And so basically, kind of, our understanding now is that in principle, using this procedure, you can create nearly perfect this RVB type state, even though, and which will be gapped and have all properties, despite of the fact that it's not a ground state, right? Yeah. Well, that's a surprise. That's for example, that's the best possible numerics what one could do. Yes, 1 over R6 apparently destabilizes in the ground state, the spin liquid, So no. So we are So this is basically the truncation radius. No, we are somewhere. We are way above, right? Basically we should not be. This window spin. Yes, we're above the red line, but nevertheless, we see a broad. But in practice, we see spin liquid like, in a range which corresponds to much shorter kind of radius. And the reason what I'm saying is that the reason is this transition into this this valence bond state is the first order. You just, if you go with the finite, if you start with the right state and go across phase transition with the finite speed, you just don't see it. It's exponentially small gap, right? You never nucleate it, exactly, Yes. Oh, yeah. So for the expectation, it's a good question. So basically, they're effectively the same length, right? So basically, what you do for the open, basically, for the open loop, what you do, you just look at kind of at a half, exactly. So they are the same length, exactly. Yeah.
So once you reach quarter filling, once you have the diamond stage, there should be an effective diamond model. And what is it? The effective diamond model, I think, should be like very high order, like 6th order in omega.
Yes, you can derive perturbation theory, right? And indeed, in perturbation theory, it's like 6th order kind of. But of course, all of these things happen in a kind of non-perturbative regime, right? It happens when omega is on the order of delta, right? So that's where this, you see this. This is a region. Basically, this is a region where delta over omega is like basically, something like 3, right? And your perturbation theories, of course, would be valid when delta is much larger than omega, right? Yeah. But there is an effective model you can derive. Yeah. So this BFFM is a kind of another parameter. And of course, the kind of the thing is that, it's 0, so it's sort of a little bit odd, but, to call, but, it is actually, what is kind of interesting is that if you look at this BFFM, then, what you see is that, okay, so it should be, basically approaching, both of these things should approach 0. And you can ask how, for example, it scales with the system size, or with the loop size, and actually what's kind of nice is that, so here for larger loop, right, it becomes, you see this becomes kind of more flat, right? It approaches kind of 0. So it kind of has a right scaling, but you can, for example, estimate density of anyons from this, you can do all of these things because we have all of this information, right? But, but it is kind of, it is a funny, it is, I must say, it is unsatisfying to call it order parameter because it's 0, but, so, but there are potentially other ways we are thinking about now. So for example, one way to define an order parameter is kind of by using the ideas from quantum information science, by seeing, for example, can you pair anyons, right? To kind of recover the order in the entire. So is it sort of the state that you create, is it, can you pair anyons in the right way to kind of see emergent order across the entire system? So there could be another ways. This could be other ways to define order parameter. Yeah, exactly. Exactly. And we are working. The only problem is that once you start pairing anyons, like it's easy to overcorrect basically. So one has to do it in a clever way. But I think we have some work in progress, which I think looks very, very promising. And I think there would be another way to actually using the ideas of quantum error correction, to do it. So, okay, I think I should probably stop. But let me just give 5 minutes, maybe concluding remark, and maybe also inspire you a little bit, so more, so okay, so all right, so with this, okay, so all right, so okay, so okay, what we could, with this kind of observation of spin liquid, of course, could not resist ourselves to make a small baby kind of topological qubit, and the way how we did it is we made a system with non-trivial topology, basically, removed 3 atoms in the middle. So it's the smallest possible hole, which kind of makes it, this, like donut coffee cup type of thing. And, in this case, actually, it turns out you can already define, the system, in this case, the state will be ground state should be doubly degenerate. And, you can define this kind of 2 string operators, which will not commute, right? Because they intersect only at one point. And basically what we expect is if we do this kind of quasi-adiabatic preparation, we should prepare the state, the superposition of like 0 and 1 logical state, and indeed, when we make these measurements, we basically see that our state has indeed final overlap with this psi plus state. So it's kind of a first steps, if you want, towards this topological qubits. But you kind of see that, of course, it opens a lot of exciting directions. So you can now start making these, holes and moving them dynamically by basically using laser beams and braiding things and so on. And this is actually something which we're exploring. All right, so I will not talk about combinatorial optimization, but just to kind of conclude, let me tell you about one other project that we are working on. And that project goes very much towards kind of building a full-blown error-corrected quantum computer. So what I told you so far is basically our, okay, now I'll see. So basically I told you so far about, all our work included encoding quantum information in ground and Rydberg states. So Rydberg states, as I already indicated, they live for a finite time. So, I mean, they interact strongly, but, this encoding has some limitation. But of course, in atomic physics, we know that we can encode qubits also in hyperfine states. And then the lifetime is basically limited by a vacuum in your chamber. So in our case, it's actually it's a few seconds. So, but the key thing is now with the atoms encoded in the ground state, we can rearrange atoms. We can move them around while preserving quantum coherence. So up to now, what I've done, we arranged atoms classically, right, and then started, exciting the quantum states. But now, instead of that, what we can do is we can actually encode the information in these hyperfine states and then move them around while preserving entanglement. So here is one example. So we start with pairs of atoms and entangle them, by exciting them in Rydberg states and then bring the excitation back. And then we can measure that they entangle by just looking at fringes, directly here. Or alternatively, we can just take these atoms and move them far away, basically across essentially the entire field of view, very quickly in a fraction of a microsecond, very small time compared to the lifetime of coherence, and then basically see that entanglement is unchanged. So this kind of moving atoms have been discussed for a long time, in principle, theoretically, but actually when we try it experimentally, it works extremely well. And basically there is zero cost to that. Okay, what can we do with that? Now we can imagine, doing, having an architecture where we basically, arrange the atoms, execute some gates with nearest neighbors, and move atoms around, execute another set of gates, and etc. So let me just give 2 quick examples. One of them, generation of the graph states, in particular of a cluster state. So cluster state is a relatively simple state where you basically entangle, you do controlled phase operations on nearest neighbors, like this is a circuit. So we can do it in just 2 steps. So we can start with atom pairs and entangle them like this by, doing controlled phase gates, then just move one atom in a pair to its nearest neighbor, do another set, and then we actually also can move the atoms to a separate zone where we can do rotation or read out. And here, for example, we can measure stabilizers of these states, indicating that we prepare the entangled state. But you could say, oh, this cluster state, you can do it in other ways. It's very simple. Can we do something a little bit more interesting? So in the spirit of this spin liquid, so how about we now will try to prepare a toric code state, but on a torus? That kind of seems hard. So, well, it turns out that this toric code state can be actually formulated as a graph state, except for this graph should have a non-local connectivity. So it should, in this graph, what's shown here, the black are data qubits and this red are basically ancilla qubits, and you see that they are connected kind of across this array. So to to create a state, what we used actually one old idea from Peter, so who was San Ignacio, who early in 2000 proposed this idea. At the time there was still magnetic hard drives, and they said, oh, what if we replace a hard drive by a qubit, And I mean, they kind of, at the time, they wrote a lot of visionary papers, but this one, I think, was considered too visionary. People said, oh, God, this will not, never work, So we actually implemented exactly this idea, except for instead of one qubit, we move the entire array. So here is the movie, which will show you how we make this kind of toric code on a torus. So in this case, we'll have 8 ancillas, which we will entangle. These red dots are controlled Z operations. And basically, we move them around. And they basically interact with the array just to enable this connectivity. See, we move them far away to, and then at the end, we have, ancilla readout. So with that way, so we actually create a toric code state, which is actually an error correcting code. So on a torus, you can encode 2 qubits. You encode the qubit along the long direction and along short direction. And here is the measurement, which basically indicates, in this case, we create an X state. So both raw data and error-corrected data. And what you see here, for example, one of these qubits is protected by a longer dimension. So it error corrects to 1. Another one error corrects not quite to 1, but still, a good fraction. Okay, so maybe this is a good point to stop. So as you see, this is kind of very exciting time where we can really start now exploring this idea of fault-tolerant quantum computing. And the key thing here is that to create these 2 logical qubits, we use a number of control knobs, which is basically on order of 1. So all what you need is to basically move this ancilla around, which is basically done by programming essentially 2 voltages. So there is also some other exciting direction where you can actually combine analog and digital quantum dynamics, and it's actually very much inspired by work by Adam's work while he was in Marcus's group. But maybe I can leave it to a question and answer a question. All right, with that, I'm sorry for running over time and for the technical problems. So here is a summary of my talk, and I would like to thank you for your attention and I would like to also thank all these people whose blood and sweat resulted in this work. Thank you.
Thank you, Misha, for this impressive and amazing results. So we had a lot of questions during the talk, but if there is a pressing urgent question. Maybe I could ask about what you were going to say about Adam.
About hybrid?
Yes.
Okay. All right. So there are 2 parts of the talk that I did not give. So, but this one is actually short. So the question here that you can ask is the following. So can we now, because we can basically arrange atoms, do coherent manipulation, then store the coherence and move them around, can we imagine now not just doing digital or analog quantum processing, but do a hybrid version? And the answer turns out to be yes. So as an example, what we did, we measured entanglement entropy in many-body dynamics. And the way how we did it, was the following. So we started with 2 chains of atoms. which we then excited into Rydberg states and, kind of did some dynamics experiments. And then after this dynamic experiment, we stopped them and then we mapped them into the hyperfine states. And then we basically moved the atoms in this way to bring the atom pairs nearby. So initially we had basically 2 copies of the state. We bring them together, and at this point we can just do Bell measurements here, which actually basically, you can use to extract things like purity or entropy of the state. And so basically this, this expectation of a swap operator is essentially you could evaluate by just measuring, the probability of singlet. So if the 2 copies are identical, right? So if basically 2 states are identical, you should never have singlets, right? And so here is, the example. So we have 2 chains, evolve them, and then we measure. And then, for example, here is if we do a simple quench, we see how this entanglement entropy grows, and we can measure, for example, for 1 atom or for half chain and do stuff like that. And it's very much inspired by the work of Adam, well, in Marcus's group. So you can also see that our kind of state remains, very pure despite all of these manipulations. But one other cool thing that we have done is actually it's maybe too much. So we've also measured, these many-body scars, these non-thermalizing states, which we discovered in our early experiments where we did quenches and looked how system thermalizes. And it turns out there are some states which don't thermalize. And they are now kind of called quantum many-body scars. And for example, what you could do, you could just make measurements like this. You can basically see that if you start with different initial states, this half chain entropy, grows very, very differently. So some states thermalize much, much slower. And in fact, some of them are Bay area law, while other volume. And in fact, you can do things like this. You can actually study like Renyi entropy of the sublattices and so on. And so basically you can see that there are some states which kind of violate second law of thermodynamics, at least for some time. But stuff like that you can explore. Yeah. Sorry for this.
One very last quick question.
Once when the bits you measured, you gave them order of magnitude. Have you thought of other ways like measuring the entanglement spectrum?
Yeah, so in principle, with this way, we can measure entanglement entropy, topological entanglement entropy, and it's kind of on the list, Yeah.
You had also one last question.
I think it's fine.
It's fine.
Yeah.
Okay, so let's thanks one more time, Misha.
So